Hello, everyone. My name is Gab McDonough, and I'm the Educational Action Supporting Officer at ERN-EuroBloodNet, and I'm happy to welcome you to the second session of GenoMed4All and ERN-EuroBloodNet's educational program on artificial intelligence and hematology for an expert audience. And this program this year aims to increase awareness of the cutting-edge advances of artificial intelligence and its implications in the field of hematology. I'm very happy to introduce you to Professor Enrico Giampieri. The title of today's webinar or session is The Standardization, Bias, and Data Quality, focused on trustworthy, clinically relevant AI. Professor Enrico Giampieri is a professor of applied physics at the University of Bologna in the Medical and Surgical Sciences Department. He is involved in several Italian and European projects on artificial intelligence, safe and secure data management, multiomics data analysis and for biology and medicine, with particular focus on hematological diseases, patient satisfaction, and survival prediction. So, Professor, the floor is all yours.
Thank you very much for the introduction, Gavin. It's a great pleasure to be here, and it's a great pleasure to be able to share these ideas with you all. I really hope that this could lead to some interesting discussion at the end. So, thank you, everyone. As Gavin introduced, this talk is going to be about standardization, bias, and data quality with a focus on trustworthy, clinically relevant AI. So a lot of keywords in here. We'll try to discuss what they mean, where they come from. Now, for a starter, even if probably um, given to the audience, what do we talk about when we talk about AI in healthcare? How can we use it? What are the limitations? What are the problems? And how can we move them out of the way to actually get forward? Now, if we look at the World Health Organization, and especially in the guidance documents, we can see that they classify the AI health application in mostly 4 different fields. The healthcare, so basically the down to the ground actually uses for diagnostic purposes, prediction, risk stratification, identification, decision support systems, the biomedical research, so all of the background applications of AI, for example, repurposing or identification of genomic variants, exploitation of big data, and so forth. And 2 more that are the health system management. So everything that goes into the administration, the logistic of the system, and the public health and public health surveillance. So, for example, from the last few years, disease outbreaks, pandemics, health promotion, and so forth. Now, this discussion that we'll have will focus mostly on the first point, and we will talk a little bit about the second because it's quite related. Now, these, of course, are really interesting proposal for uses of AI. If we could have strong AI, reliable AI that work alongside clinicians to provide information in understanding complex cases, in taking into consideration complex situations for patients, that will definitely be a huge improvement. But can we actually do that? Now, this is the question that needs to take into consideration 3 big elements. The first, of course, are the benefits. The benefits for the patient. So, for example, a better outcome of care compared to simply working with a clinician. An improvement, a benefit for the healthcare system. So, for example, having more efficient processes. And for society as a whole. So, having higher access to healthcare. One of the things that I worked personally, for example, was at-home diagnostics. So in case of some patients, sometimes due to frailty and so forth, it's hard for the patient to actually go to the hospital to get the care that they need. And so in some situation, we can try to bring the healthcare system at home. Now, of course, this come with costs, come cost for patient, for the healthcare system, and for society. Well, for the healthcare system, of course, we can be talking about monetary cost, but then we can actually be talking about increasing complexity. For example, if we're asking to a clinician to use AI, these AI need to be usable. It shouldn't be an additional burden for the clinician to use. Ideally, it should be something that makes their life easier. But we also need to account for the potential risks that we have whenever we introduce an automated system in the loop. And basically, these potential risks are going to be the focus of everything that we're going to talk today. What these risks are and how can we try to overcome them, and what processes can we put in place to make sure that this is actually plausible. Now, at the end of the day, to actually decide if we will use AI for certain application, we basically need to focus on 4 points. The first one is that we need to have for this AI to be with low absolute risk. Now, this idea of risk will be, I will use this word until it loses meaning into my mouth, but is one of the main criteria, for example, that the Europe use for evaluating what kind of uses on what kind of limitations AI have. We will talk about the AI Act a little bit later, but for some applications, the risks are deemed too high to be used no matter what the gains might be. Then we need to have something that is, of course, high quality, so it can actually provide a good benefit, a reliable benefit. And we need to have the cost to benefit ratio to be useful. So we are willing to pay a price, but this price should pay us back with some improvement. But most we want these estimates to be believable. This is one of the big points that we will touch. The problem when we talk about reliable AI, trustworthy AI, whatever we want, is if we evaluate risk in our model, and if I say my model is very low risk, how can you believe that my model is actually low risk? I mean, if you're doing with some kind of medication, then you know that there are processes in place to actually make sure that these medicines are safe and are effective. And one can verify that there has been all the steps in clinical trials to make sure that this is the case. And basically, the is that we want to get there with AI as well. How to get there is the big part of this. Can go wrong. First of all, so we will talk about risks. Okay, so what can go wrong? Well, we can have for first privacy breaches. So whenever we're working with patient data, we can risk leaking sensitive patient data all around the place, both at the training phase, so when we want to create the AI, and at the usage phase. Then we have, of course, the possibility of worsening clinical outcomes. So if our AI has a bias that make it uh, perform wrong prediction, we might do worse than just not using it at all. Then we might have false improvement. We might have the illusion of having a system that works and not having really good perception of what the actual damages might be. Now, this is often a systemic problem. So if a system works very well for 95% of the population, and we keep track of the damages that we're doing to that 5% that we are actually damaging, because more often than not, that 5% is the one that is damaged because it's already under evaluated in the training system. Then we have, of course, system inefficiencies, because If our AI is, for example, recommending exams that are noxious to the patient or are very expensive, that can create issues. Now, when we want to evaluate this risk, what components should we take into consideration? We will find these again and again during the presentation. There are basically 3 points that are the data that we use for the training of the system, there are the algorithms that we use, and then we have to evaluate the processes that we use to accumulate the data, process the data, pass it through the algorithm, train it, evaluate how good the training is, and then deploy it in the system. Now, how can we actually try to make sure that these things actually are, as we intend them to be, trustworthy? Well, we need all of the steps, all of the things that we do. We want them to be legitimate, moral, and robust. With legitimate, of course, we want them to follow the EU legislation. So we are starting to have a good amount of EU legislation about how to treat data, how to treat AI, how to treat algorithms. And of course, there is a lot of read about healthcare. Be sure that the system that we're using are actually following all of these regulations. Now, I'm going to go out of a limb here and say something that probably is not that common. But yes, it is true that we do have a lot of regulations here in Europe for data management and AI, and they definitely add cost and complexity to all the processes. But I actually think that they are really well made. Okay. So, yes, they are cumbersome, but they are working from a position of uh, trying to limit risks that sometimes we cannot predict. And so we don't have an upper bound on how much damage we can do. And so it's kind of necessary to follow all of these processes. Then we have morality. Now, this is intertwined with the, but basically we want to be sure that the things that we do are following ethical standards. Ethical standards in all of the steps that we do. And this will become apparent later when we talk about biases. And lastly, we want robustness. We want a system that works when it's supposed to work, but when things are not supposed to be working, it's able to fail in a safe way. And this is something that I think is still in the infancy in the field, but it's very important. For example, I still don't see very many systems that when they don't have enough information for decisions, rather than say, I don't know, they give some prediction. Yes, they put some confidence interval, but sometimes I don't know or I need more information are legitimate answers. And we need our system to be able to provide them. And we need our system to not freak out if they see something that shouldn't be there. Okay. Now, there are in the last 2 to 3 years, few publications that are actually going into details on how to actually build up trustworthy AI. Okay. And they basically split the distinction between basic design, so the data and the algorithm, as I was saying before, and the part of application. So all the processes that go from building the system to deploying the system to determining who is responsible for it, both at all the steps, including if things go wrong. Okay, I will focus on the first part, the data and the algorithm, because I am not a lawyer, I am not a logistician, but I will give some points in that direction. We want to focus on data and items from the base complicated. Now, this is an actual presentation from one of our papers process of the prediction for training of a model. So basically, we try to make a
Professor, can you hear
model
me?
for predicting
It appears that your sound is having a little bit of
language.
issue.
Okay, I hope that the connection is working. Thank you very much, Gavin, for the explanation. Now, as I was saying, we have, of course, complication in the model. Even if we consider a relatively simple model, the overall pipeline can be very complicated. And then we have a complexity at the level of data. We have many type of data. We have both structured data and we have metadata and we have non-structured data such as text and images. And these data can have issues, might be poorly annotated, might be with defects in the collection, might be poorly might be dishomogeneous and so forth. So we need to account for all of these things if we want to move forward. And on top of this, as I was saying, we need to follow the EU guideline and specifically what is referred to the European data strategy. Basically, it is the general strategical direction that the European Union is going through with, and is composed at the moment from the General Data Protection Regulation, the GDPR, and the that is already active, and the AI Act and the Data Act. They will start to be in function in the next couple of years. So the Data Act will start to be active from September 2025, the AI Act from August 2026. Now, these two will have strong implications. The Data Act is basically formalizing the exchange of data, especially between private and public, and under which condition the public system can require private data for the public good, and the data exchange with extra-European countries. Now, one of the consequences of the Data Act might be the invalidation of the previous informed consents. Now, this is probably going to be a big effort that we will all need to do because at the moment we're still not sure if under this new regulation, the previously collected informed consent will be actually still valid. Uh, for the case in point, the other one that we are interested in is the AI Act. That is another regulation that even more than the GDPR employ a risk-based approach, basically stratify the different applications of AI based on different risk levels. And some of them are deemed too risky to use. For example, social scoring, those things are outright banned. And some applications are defined as risky or high risk. And based on that, they give guideline on how to perform it all. Other principles that they work on top of are the idea of transparency. So our AI needs to be explainable, needs to be understandable. The principle of reliability. We want our AI to be reliable in how it works. So if it goes wrong, it should go wrong in a sane way. We want to minimize the data used. Now, this is a strong point because, especially in the last few years, AI has been in the center of the storm about how data is collected and how the use of protected data and so forth. And lastly, the idea of responsibility, making it clear who is responsible for what in the pipeline. Now, there are, alongside the previous existing certificate for security, for example, ISO 91, ISO 90,000 or 27,000, there are new framework for security from the ISO IEC and the IEE consortiums that are writing both technical reports and new standards for actually application of this AI. So from a procedural perspective, this is basically what we have to refer to. But this is all I wanted to say about the procedural part. Now, on to the more technical aspect. As I was saying, there are two different sides of this equation that are intertwined but can be discussed separately. And the first one is the idea of biases for the data and the algorithms. Now, the first one is where does this biases can come from, especially if we talk about the algorithm. Now, the first one, of course, there can be imbalance and distortions in our data. So we can have quality data issues, for example, if the data are poorly collected and unreliable. We can have problem of the drift, meaning drift. So the data of today might not be representative for the data of tomorrow, or the data that has been collected in this country might not be generalizable on another country. We might have information uncertainty. So might not be certain on some part of information. The classical example that we'll talk again is segmentation. So identifying some part of an image that, for example, identifying what is the tumor inside a CAT scan or what are the cells inside the cytological slide. Now, each individual clinician might have disagreement on what is the tumor region, what are the metastases. And so we might have trouble actually finding that. Then we actually can have problem with the algorithms themselves. And more than that, we can have problem with the optimization criteria. So what are we trying to achieve? I will talk about that a little bit more. And with the assumption that we do about our data. And lastly, we can, of course, have problem with human procedures. If we have problem with the humans working in the system, that can lead to unexpected outcome. Now, to go a little bit more into the detail, when we talk about algorithmic biases, we can distinguish between human-induced and data-induced. Now, the distinction is not always as clear as it can be because, of course, data are collected by human and the procedures are designed by human, but in the end is the data that is being processed, but this is the usual standard that we can work. Now, we usually talk about data-induced bias whenever the training data that we use to generate our AI is inaccurate, non-representative, or insufficient. Now, this can be a problem even when we think that our data that we collected is representative, is accurate, is sufficient, because it might be inconsistent. For example, a typical example is that if we're trying to do identification of pulmonary nodules, one of the gold standard for the diagnostic purposes is the biopsy, but not every patient in real life will have one. So our system might have trouble because even if we train it on perfect data where every patient will have its own biopsy, they might not have it in the clinical practices. So we need to account for these kind of problems. Then we can have problem with the human-induced bias. Now, these are sneaky because these are our own biases. Okay, so it's often hard to identify things that we don't know. For example, idea of moral perception or relevant interest. When I talk about moral perception is let me deviate for a second out of these issues. A famous example about human-induced bias has been found, for example, in criminal cases. So when the AI was using the previous data to actually predict the future behavior, for example, in hiring. Okay. Now, if the system is trained on previous data, the classical example is like it was actually the algorithm for hiring were biased against women in a lot of companies simply because the previous hires were biased and so they hired mostly males But most importantly, the people that took the data and selected the data and evaluated the algorithms didn't actually think about checking that because they were sharing the same biases that generated the data. So they didn't realize until somebody from the outside went and checked that they were actually creating something that was biased. Now, this can be intentional or it can be unintentional, but this is something that needs to be considered, especially because this is something that can be self-increasing due to reinforcement process. If I see that my system is performing a prediction and I don't agree with the prediction, I might deem some to be mistaken and remove them. And therefore, lastly, we have the problem that sometimes it's hard to detect what are we actually doing because we're working with black box and not often we can actually detect what is actually being shown. For example, it's known that for melanoma, certain phototypes are underrepresented and are more complex, especially the dark one. And so given that the data sets are all trained on very light-skinned kind of phototypes, they are performing way worse when we go and consider uh, darker types, or sometimes the usage of healthcare cost rather than the actual disease. So, for example, how much effort has been put into the system for different categories, and that is known to lead to some discrepancies. Now, this last case, the case of the dataset distortion, is probably the easier one from an outside perspective to understand, but it's still quite tricky. Okay, and there are basically two different cases that we might mostly find. One is that the dataset is unbalanced. Okay, so if we have a collection of data that, for example, overrepresent men over women, our system will be poorly trained on the women dataset, and therefore the performances in the future will be worse. This is a kind of bias that is quite common because on the other side, not always we know what kind of stratification we may need to do. Now, this is often referred as the Simpson paradox. And that is something that basically means that sometimes we're not aware of certain stratifications that we might need to perform on our data. And this stratification might have strong clinical effects. For example, classical example that was used to explain the effect of this in clinical studies was the effect on treatment on kidney stones. There were all the type of kidney stones, but given that they were differently prescribed to different kinds, the overall result seemed to favor the worst one. Okay. And these are kind of biases that we have in the system that we need to take a strong look at to actually try to identify. They're not trivial. The next one is our assumptions. Often our assumptions about our models are wrong. A classical example of this is the idea of truncations. If we do not collect all of the patients in a real random way, we can have models that do terrible, even if the data is correct. A typical example is the case of self-selection biases. So if a part of the population is more likely to get tested or to take or to have access to the healthcare, then they will be more represented. But I might completely lose part of the patient that might be in a worst case scenario and still not get tested. And so my system doesn't know that they exist. And if I don't take that into consideration, they will perform very poorly. And lastly, there is a problem of being able to describe what correct look like. Okay. This is a very common problem when we talk about computer vision, because sometimes it's hard to find a way of explaining what the right thing is, especially if we're talking about histopathological slices or CAT scans. Determining exactly what the ill part is, what the infected part is a blurry thing. It's not easy to actually describe our processes, our mental process to actually determine what these things can be. And so testing for all of the cases in which these systems can perform poorly, that becomes very difficult. Now, in other cases that we may have that can impair our ability of actually having good, reliable system is the so-called specification gaming. And this is, in my opinion, one of the most understated cases for the problems in AI. Okay. And that is the fact that at the end of the day, even if we have good data and we have a good algorithm, we still need to tell the algorithm what a good solution look like. And as I was saying earlier, most of the time, we're not really able to fully grasp with a mathematical function what do we mean when we mean meat. Okay? And so we rely on partial solution. For example, if we're looking at again segmentation, so identifying a region inside of an image, we might say, well, these two images just need to be with a certain amount of difference between the pixels. Now, these can lead to a huge amount of trouble because the system that we're trying to perform are optimizers. Okay. Now, there is a whole field of AI safety that really gets into the depth of this, but there are some lessons that we can take from this. And one is that optimizers will wreck the hell out of any request that we do if we're not really careful in how we specify what correct means. Okay. And I would like to point out that this is probably one of the cases where the collaboration between data analyst and clinician is most critical. Because at the end of the day, clinicians are the one that knows what correct looks like. But data analysts are the one that knows how to express for the AI system, how to express mathematically that correctness. And the problem is that both of these specialists lack the language of the other. And so that means that there is this incommunicability, and that makes it extremely difficult to actually specify to the system really that we want something specific and not something else. And the result of that is that it's infamous how often AI system basically learn not to give the answer that we want, but to give us the answer that we say we want, that there is a difference between the two. Now, this is the subject of jokes and whatever, but a classical example that is used, then we're going to go into the medical ones, are for image recognition. For example, classical one is like, we want to distinguish between wolves and coyotes or different kind of animals. Well, the systems actually at first learned not to look at the animal. They learned to look at the background. Well, because coyotes were always photographed in drier, summery environment, and wolves were photographed in forest with the snow. And so if there is greenery and snow, then it's a wolf. If there is greenery and rocks, then it's a coyote. This is not what we wanted, but we just asked the system to learn to discriminate in the data set that we provided, which were wolves, which were coyotes. It did it, but it didn't learn what we wanted to learn. Here are some cases in clinical AI where these kind of problems actually arise. Okay. For example, in one case for COVID, AI learned to distinguish basically between kids and adults because the data set was unbalanced in the number of kids. So to predict the severity or the presence of COVID, the system basically learned to look at age of the patient. And yes, it's a kid. In this data set, kids are less often represented with COVID, so we don't care. In another case, it learned to distinguish between standing patient and lying down patient because basically there was this um, unaccounted for correlation between those who were lying down and those they're typically more healed than those that were able to stand up. So the system wasn't really looking at the level of infection. It was just looking at, well, if it's laying down, clearly it's because it's very healed. And so I'll say that it's very healed. And even better than that, my favorite example is that in one case, the system was actually was not even looking at the scans. It was actually looking at the font that was used by the machine of different hospitals. Given that different hospitals had different incidents of severe cases, then by looking at the at the font of the text that was included in the scans, then it was able to predict from which hospital it was coming and therefore what was the base rate of severity. Okay. Based not on the actual image of the nevus, but based on the presence of a ruler. Because when there is a big, bad looking nevus, then usually clinician put a small ruler in that. And so if the system saw a ruler, well, that clearly is a bad sign. Now, this brings us to the idea of creating explainable and reliable AI. I'm a little bit overrunning on time, I'm sorry. And now this part is, I'm not going to go into the details, but the idea is that when we want to talk about explainability and reliability, we're basically trying to get information about how the system is performing the prediction that it does. So for example, if we're looking at an X-ray scan, we can actually train the system so that it doesn't only give us the prediction, but it also highlight which part of the images were important to make the prediction. And from this image, for example, it was trying to bursitis, then a bursitis of the shoulder. Then if we see that the system is giving a prediction, but is not looking at the shoulder, then we know that even if the performances might be reasonably good, it's probably not looking at what we think it should be looking. In this case, the shoulder. Okay. Now, what are the limitations of this approach of explainability and reliability? Well, first and foremost is that these models are, of course, more complex. So that means it requires more data and it requires more computational power and it requires more expertise. Even worse, there is always a trade-off between accuracy and explainability. So whenever we try to force the system to be able to explain to us how it performed some predictions, we're basically limiting the approaches that it can follow to the human understandable ones. And so we always end up losing a little bit of accuracy. And lastly, we have a problem of human and AI interaction because using the system require knowledge, require expertise that we might not have. Because we show some if I, as a data analyst, need to program some of these systems, I need to be able to understand what are the things that the clinician looks like. And when I output the statistics for how the system is actually looking at the system, the clinician needs to be able to understand what those statistics mean, okay? If I have a heat map like this, then it's relatively easy, but sometimes there are more exotic way of expressing that, and so we need to have a shared language. Now, I'm trying to accelerate a little bit. I'm really sorry. Sorry, Gavin, how much more time can I take for the explanation?
I mean, I think you have as much time as you need, so it's an excellent presentation. So whatever you feel comfortable with.
Okay,
And
thank you
plus,
very
this will be
much.
recorded, so.
So the next point after we talk about the algorithmic side is talking about data quality. Now, data quality and access, because these two things go hand in hand, okay? Now, the first problem that we have is that whenever we want to train a system, we need to have the data, but these data need to be harmonized. What do we mean by harmonizing the data? Well, the problem is that more often than not, we will have data that comes from a plethora of different sources. It might be internal or it might be external. So for the external case, we might be collecting data from different hospitals, from different centers. But even in the internal case, we might have data that's being collected by different machines or under different clinical situations, so with different pathway of cares, or even in different times, so the procedures themselves were different from patient to patient. If we rely on our data to have some kind of structure, for example, of DICOM data, but we gather some data from 30 years ago, we might not have the DICOM data themselves. Okay, so we need to rely on different kind of structured data. So harmonizing the data means taking all of the data that you have and bring them all into the same format, because one of the important things about all of the systems that we have currently until we find a different approach is that they need reliable structures of data. So the same model will always and only work on the same kind of data that it has been trained on. I mean, trivially, if you have a data that is being trained on CAT scans, so on images, you cannot pass it a biopsy scan and expect it to work. It's just a different kind of image. So what do we need to actually, sorry, what are the problems that we can find in harmonization? Well, the first one is, of course, heterogeneous data sources. Different kind of sources can have different data. So, for example, different machines can collect different data about the patient. Some can report, for example, if I'm talking about biopsy scan, some microscopes will save the magnification level, some will not. Some will write it in a different format. Some will write data, so dates in a different format. Americans and Europeans read the dates differently, and we need to convert from one to the other. Then we have the issues of privacy, because if we're collecting a lot of data, we need to actually make sure that the data we collect is respecting the privacy requirement that we want. And so we need to remove data that can allow the patients to be identified. So how much can we take away and how to do it? It's a whole kind of worm. We don't have time to go into that, but um, anonymization procedure is a whole field of research. There are methods like anonymity and differential privacy, or even ways of performing calculation without actually looking at the data themselves. Then we have problem with biases, meaning that in similar ways as we were talking before, different um, different systems might perform slightly different baseline measurements. I mean, if any of you ever worked in lab, you know that the calibration of your instrument might be slanted. And so even if it's very small, once you have data with a lot of different kind of data in it, this difference, even if each individual one is small, when put them together, can completely separate the different sources of data. And that will become a very informative parameter that we don't want our machine to rely upon. And that might lead to the problem that we discussed earlier. Then we have problem in the subjectivity. If we're using some kind of Likert scale, for example, a qualitative assessment of the severity of the state of the patient, different clinicians in the same institute and different institute will have different guidelines on how to evaluate it. Then we have difference in, problems due to the complex logistic in data collection, because we're talking about trying to gather data out of a human being. If you want to have an MRI scan, we need to actually book an MRI and have the patient go under the MRI, but they might not be able to. Or if you want to have a blood work, the results might be lost, or there might be a problem, or many different possible ways that have nothing to do with the actual data system or anything else, but just coincidence because real world is messy. And lastly, and but not least, is balancing patient need with accuracy and cost. Because of course, I can tell you from a data analyst perspective, if you ask me how much data is needed for the prediction, my response will always be more. You have a CAT scan, why not an MRI? You have the blood samples, why not also genomic? You have clinical information, why not also a lifestyle questionnaire? Each one of those will bring new information on the table, but it's also asking more to the patient. If we're asking them to take a CAT scan, that means more dose. How much of that dose is actually useful? And if some places change the evaluation, for example, some machines are calibrated to perform a higher dose or a lower dose, that may change this evaluation from center to center and availability. Okay. Now, how can we try to improve on this? This is one of the, I honestly think, harder problem nowadays. Okay. Well, one of the first point is having shared common data model, things like HOMO or FIRE. So way of representing the data that are uniform across all the different centers that are performing the study, so that whichever center is sending the data, the system will be able to work on that, but also each individual center doesn't worry about which specific format the developer choose for their model, because they know that if they format their data in OMOP, all of the being a common data model, all of the system that relies on OMOP will accept their data. Then we will need some form of standardization of the acquisition procedures. Now, this is a logistical nightmare and probably also a clinical one. But as much as we can try, up to a certain point, we need to have reliable information about the patients. It's the same patient, we need to have comparable data if we want to have comparable diagnostics. And lastly, we need to agree on what our analysis targets are. When we talk between clinician and data analyst and different clinician with different medical interests, we need to agree on what are we trying to achieve. Because remember that due to the European guidelines, we only want to use the minimal amount of data that we can get away with to actually perform our goal. So yes, it will be lovely to say, especially for us, let's collect everything and let's use everything. but we can't. Okay, we need to have a shared goal in what are we trying to get and work from there. Now, an important step in this whole system is the idea of documentation. Okay. Now, this is something that, especially in the programming culture, is a little bit more common, but in the data collection is still very new. So the idea that whenever we collect some data, having just the data means nothing if we don't keep track of everything that went around when we collected the data. Okay. Now, I hope that most of you have at this point heard about the idea of fair data. So the data that are fundable, accessible, interoperable, and retrievable. That is not enough. Okay. Because to really understand the dataset, we need metadata. And data without information about the data is just random numbers. Okay. If I just say tree, tree by itself means nothing. It's not information, it's a number. If I say that the patient is 3 years old, or that the patient has 3 child, or that he had receival of the metastasis, those are very different informations, okay? Or if I say, yes, the patient have a tumor that is 3 millimeters wide, but they don't specify how I did the measurement of that width, okay? How did I use the ruler to perform it? All of this information are crucial to give meaning to that tree. Remember that the system that we're using, the AI, is dumb, okay? So it's only seeing 3 as the number. So we need to encode that meaning externally. It's not something that the system itself can do. So, for example, in the last few years, there's been a strong push, for example, for questionnaires, standardized questionnaires that collect informations. Now, I don't think that which one uses is as important as the fact that one uses one of these questionnaires. For example, in the article data sheets for datasets, they propose this one, and these are the macro topics that they actually go and for the data collector to fill. And on each one of those, there are many, many questions underneath. But for example, what was the motivation of the study? Why were you collecting those data? Because that can show, for example, possible biases. What is the composition of the dataset? How many patients? How are they stratified in different groups? How were they actually collected? Sorry, that's the following point. How were they actually collected? So were they volunteers? Were they randomly picked out of hospital? Were they paid volunteers? Study mixing up volunteers and paid volunteers leads to terrible results. It shouldn't, but it does. Then what process of pre-processing, cleaning, relabeling has been performed? How the data were cleaned? Have been already performed on this data. Now, this I think is one of the most interesting one of these questionnaires, because all of the other informations are more or less static. How did I collect the data? It's one and done. But this is actually making it a breathing, living document. Because every time I use this data to perform a new analysis, then I should keep track of that and the results that were obtained. Okay. This is basically the other side of the clinical trial registration idea. So if I try to use the same data for a lot of different studies and torture them enough, sooner or later they will confess. So keeping track of how those data were used and what results were observed, it's important. Then what are the distribution rules? Who can use them? Who can access this? What legal restrictions that are to their use? And lastly, maintenance. So what are the maintenance procedures for data? For example, if I discover a mistake, a mislabeling in the data, what step can I take to communicate to you that there is this mistake? And do you have any procedure to inform anybody that use this data to perform some analysis that you discovered this mistake, and so that their analysis might need to be reevaluated? Okay, so all of these things are strongly important. Now, as you can imagine, all of these have to do a lot with procedures. Okay, and this will become a topic later on. Now, another point is quality. Okay. Now, this is a painful topic because we've been lied to. Okay. In the last 15 years, all of this idea of big data, and if you put enough data, everything will be solved. Well, that's not it. Okay. Because the reality is that, as it has always been, all of these things are still statistics. And in statistics, good data beats big data by a wide margin, because you've probably all have heard the saying that practice make perfect. No, practice make permanent. And if there are mistakes in your practice, you will make more permanent mistakes. Okay. Having bigger data sets, it's worth nothing if you cannot prove that the data that you're putting in is actually good. The problem is that getting a lot of data is easy. Getting good data is really hard. For example, here is another graph from some of our research into wound healing. And basically, the problem was identifying the region that was actually the wound. Now, we're talking about the data set of several thousand images. And now the question is, who does the annotation? Because perfection on a data set like this takes hundreds of hours. And I cannot ask in good faith to a clinician to spend hundreds of hours to actually perform the annotation. But on the other end, I'm not a clinician. I can barely identify that this is a wound, let alone identify what part of the tissue is part of the wound, what is the scar tissue, what is the healthy tissue. Okay. So, for example, for these kind of cases, we develop the some system of assisted annotation. Basically, we perform an iterative procedure so that we have some annotation, perform a trivial starting training, getting some prediction back, and basically recycling the good prediction in the training image, in a training data set, and retrain from scratch. And for example, we have seen that just with performing something like a 1% annotation by hand and 3 passages of performing these segmentations and having the clinician just go through the data set and say, this is good, this is not. So in 5 minutes, he went through the whole data set and say, this was good, this was not. And we didn't actually need it to decide case by case. In just a couple of passages, we managed to have everything segmented almost perfectly. Okay. So we went basically from hundreds of hours to one afternoon of work. But this doesn't actually solve another problem, this so-called agreement problem. Because, for example, we relied on one expert, but different experts, of course, can have different opinions about what the tissue can be. So this is actually still really an open issue. When we want to identify, we want to annotate the data, how do we make sure that the different experts are coherent in their evaluation? And if we have a disagreement, is this disagreement due to human error or human difference in evaluation? For example, different clinicians just simply think that different things have a different severity. Or are these differences representative of underlying systemic issues, for example, on how the data was collected or was presented to the expert? These things need to be solved because metric, I've lost the image somewhere, but sometimes correcting a 10% of mislabeling in a dataset performed a bigger improvement compared to more than doubling the amount of data that was in the dataset. Okay, so the data quality, data processing can have huge consequences. And remember before, how you do it, it's important. And keeping track of how you did it, it's important because if I want to verify if the labeling was performed correctly, I need to know what the procedure was to actually perform this validation. Lastly, we have the problem of data access because yes, we want to have the best data that we can. Yes, we have great labeling and all in all, but the problem is money and time is a finite resource. Each individual collection center doesn't have infinite resources and infinite patients to collect the data. So how do we approach this issue? Well, we basically have four different approaches mostly. Now I'm simplifying, but well, the first one is we can just deal with it. We only have data from our data center is the simplest solution, but of course our model will be very strongly biased, will be very limited, will have very low power, and so it's easy, but it's terrible. Okay. The other option would be to have the so-called shared data vaults. So we all sign up some form of sharing agreement, create an online platform for performing this kind of data, this kind of analysis, and everybody connects to these platforms. And this is possible, but they kind of become very quickly a nightmare because the problem is that really, truly guaranteeing that the data that we put into this data vault is secure is not impossible. Okay. I mean, let me be honest. I've seen a lot of platforms that did say, yes, our platform is secure. Yes, the data cannot get out of this platform. And then I've seen students just copying and pasting the results out of the platform. So yes, these can be critical. Now, a model in the last few years is taking a lot of attention and, for example, is part of the GenoMed partnership, is the idea of federation. So the idea of federation is that we share a single model, okay? There is one goal idea that we want to perform, and we want to train it on the data of several different centers. And the trick is that we can train the model without ever having access to the data itself. How can we do it? Well, the idea is that we can send, instead of getting the centers to send us the data, we can reverse this approach. We can send the model to the data centers, to the collection centers. They can perform a partial training on their data, and so improving the model. They can send this improved model back to us, and we average. Okay, there are several ways, but the simpler one is averaging this model from the different centers and send it back for a new range of training. So for a new round of training. By performing this back and forth, if we use good models, and this is an important bit, we can actually train the model almost as if it was in our servers without ever looking at the data themselves. So we are almost perfect from a privacy perspective. Now, this is rely on the idea that our model doesn't leak the data. For example, if our model is something like a decision tree, Well, the decision tree is basically storing the data inside the model. So sending it back and forth correspond to sending the data. But if you have a decent enough neural network model, we could actually have a model that doesn't keep track of the individual data that the system has been trained on. And so we can have a perfectly private system without this issue. I'm simplifying. There are some issues here, but it's way more secure than the other perspective. The downside of it is that each individual collection center need to have the computational power to actually perform part of this computation. Now, this can be an issue because, of course, we are asking for a hospital to have some kind of computational servers with some data analyst specialist that is able to pick the model and make it run. But these are issues that, from a procedural perspective, can be resolved. And lastly, a new approach that is coming up in the last few years is also the idea of synthetic data. Synthetic data is basically their method to the idea of federation. And it's the idea that we don't really need always to have new data for the things that we're trying to observe. We can actually use generative AI to help us. Okay. Now, generative AI in the last 5 years has exploded with things like image generation and ChatGPT and all of these kind of things. Okay. But this can actually help our system in a more subtle way. For example, if you're trying to study the identification of a specific marker in a CAT scan for a specific illness, okay? Well, you can collect you have a finite amount of resources to actually collect data. And typically, you have to collect as many patients as you have controls. So you're bleeding out some of those very scarce resources into collecting controls that you need, you don't want to collect. You would prefer to collect only patient with the interesting case. Basically, we can train the model to generate what looks like health individuals that one can then use to enhance the system that they have. For example, we can make sure to have as many controls as we want, but we can also make sure that these controls are not just random people. Okay, and I'm using random in an improper sense, but people that comes into the hospital. We can make sure that these controls are balanced for age, are balanced for gender, are balanced for BMI, are balanced for ethnicity, are balanced for all possible relevant clinical parameters to make sure that our data is as little biased as possible. Okay. And this is a challenge that we're still working on. There are many different data, and generation of each one of these data require ad hoc method. But it also have another possible application that I'm really enamored on, and that is the idea of data imputation. And that is basically solving one of the big issues of the determinization that we were talking earlier. Because when we perform this synthetic data generation, we can basically constrain this generation. We can say, I want to generate one female 40 years old with this baseline health condition. Okay. And I can do it from scratch to generate a fully non-realistic patient, but I can also do it with partial data from a true patient. So you remember earlier, I was saying our algorithms only work if all of the patients always have the same data. So if I train my algorithm on working also with biopsy, I need the system to have a biopsy as well. Otherwise, it will not run. Well, with synthetic data, what I can say is that if I have um, this clinical situation for my patient, please generate a collection of plausible biopsy for this kind of patient. And now I can perform the prediction for the patient even before they actually perform the exam. So I can still have a prediction, well, a range of predictions, have the data for that specific patient. But even more interesting than that, I could use that to guide the decision on the pathway of care. So I could generate different synthetic data for the case where this patient is actually healthy or this patient is actually ill, and see how much different exams could be informative. Okay, so this is a whole new field of research into unbiasing and refocusing the harmonization problem, and it's trivial, but it's giving um, really good results. Okay, I've talked a lot. I was planning to give a brief explanation of one cases that we worked on, but let me skip on that. So, in closure, there are a lot of challenges that we still need to overcome. And of these are the ones that has been identified as the most important from an European panel on AI trustworthiness. And the first one is improving data fusion, the harmonization problem that we were saying before, but also developing clear standards for what we mean when we talk about trustworthy AI, those problem of explainability and reliability. We cannot just say that my system is reliable if we don't agree on what reliable means. Then we need to find a good balance between explainability and performance. This is critical because, of course, we want our system to be as powerful as possible for the good of the patient, but we also want them to be as understandable as possible. And these two ideas are at odds. And so at a certain point, we need to find a compromise between the two, and we need to provide it. The system cannot provide it for us. We need to find better methods for identifying biases and mitigate biases. And here things like synthetic data will provide a lot of help. But one important thing, personal note there, we need to realize that statistics are not an option. Okay, we need to still be with the same carefulness that we always traditionally use for statistical data analysis. And lastly, we need to improve the conversation, the shared language between clinician and data analyst. We as data analysts need to be better when we are trying to work with the clinician. We need to learn the medical language of them, but we also need for clinicians to learn to understand what are we talking about when we talk about AI bias and data set annotation and all of this idea, and especially what are the pitfalls to look for. Okay, we don't need for clinicians to be able to solve the bias problem, but we need them to at least learn what are the smells that there might be issues so that they can actually defer to somebody that knows statistics and data analysis, but they cannot be involved in the loop if we don't have a corresponding part in the clinician side that is able to identify when they should be suspicious of the results. So where should we go from here? Well, one of the points is that all of the result of this has a horrible implication that we will need to increase the busy work that we'll do. We will have to do more bureaucracy, more documentation, and all of these kind of things. It's going to be a challenge. It's going to be a learning curve, but honestly, it's necessary. As I was telling earlier, data without information about the data is meaningless. And the most important information about the data is the process through which it has been collected, the process through which the algorithm has been trained. If I don't keep track of this, I have no chance of improving it. Part of this is documentation, okay? As Mythbusters said, the difference between science and messing around is writing stuff down. So we need to have documentation on data. We need to have documentation on models that we use. We need to have to improve model explainability, model reliability. We need to share the metrics that we want to use to evaluate biases and data and prediction quality and so forth. And so means that we still need a lot of coordination. These events are really important because these are the situations where you can share at least a little bit the importance of each other language, each other ideas, and we need to have roundtables and Delphis in where are we going from here? What do we want to achieve? How can we measure it? What are the risks? How can we describe and collect our data? How can we model it? Okay. We need to sit down and try both with the data analyst and the clinician and the stakeholders, trying to pinpoint all of the problems. And to do it, we need shared understanding. Okay. All right. That was all. Thank you very much. I'm really sorry about taking all of your time. And if there's any question, I'm here.
Well, thank you very much, Professor. That was an excellent presentation. And thank you, everyone, for sticking around as well. If there are any questions, now is a great time. And I know, Professor, that you have a very busy schedule, so feel free to take as many or as few questions as you prefer. And if there's a particular question that sticks out, just let us know. So,
Okay, so I'll confirm that. Okay, what do you suggest? What can we do against bias in data? Well, I would say the two most important things are agreement in what we want to achieve, because that's often a problem, and planning. Often what we have is that data is collected and then we start asking questions. And that is often something that it leads to problem, because if the data is not tailored for the question that we have, it's easy to collect data in a way that does not um, compensate for random issues. If we're trying to balance, for example, the data set, balancing is not an absolute property, is a property that is depending on the important parameters that we want for a system. And also, I mean, this is all story, but it's worth repeating. All of the stakeholders, all of the analysts need to be involved from the start. It's not possible to collect some data and think of an analysis without consulting with the people that actually will need to do the analysis, and with the people that will be affected by the analysis. So all of these parties need to be involved from the start. And the second part is our responsibility as data analyst, learning to perform this thing. Still, the problem is that there is a low barrier to entry to perform the analysis, but learning to actually check for biases is something that statisticians and data analysts has been performing for a long time. it's a whole new set of skills, and one cannot improvise to perform those. One need to have a preparation though. So I'll be honest, running a neural network nowadays is something that one can learn to do in a couple of days. Okay, it's honestly easy. The problem is everything around getting the data, annotating the data, and understanding where some of the biases, some of the pitfalls can be. Now, for the next one, how to deal with missing data which introduce the bias. Okay, these well partly goes together with the previous question. So we want to make sure that we have a good understanding of which data might plausibly miss and how that can affect our result. Now, we can try to minimize this effect in two different ways. One is with actual analysis. For example, one thing that we try to do when we work with this kind of data is simulate what is the effect of non-random missing data. So for example, missing data because there are specific circumstances of the patient. For example, they come from a specific social background, and so they're missing some data that are not just randomly missing. How much that affect the performances? We can simulate that and use that to have a have an estimate on how much that could impact and what the level of bias that could be. Then there is the point of measuring, as we were saying, having some metrics, some standard procedures that we can perform to assess that we're not leaving stones unturned when we want to evaluate these problems. And lastly, as I was saying, we have technological solutions that are, for example, generative AI, the synthetic data I was talking before, so that we can make sure that when we generate this data is as unbalanced as is balanced as possible. Sorry. Again, we can perform this kind of test from a simulation perspective. So if we have patients that have full data and we remove part of this data, we can see how much bias that introduced, and if we replace that fake missing data with synthetic data, then we can estimate how much our uncertainty or bias get introduced. Next one, is it recommended or mandatory to inform patient when their clinical data might be used to train AI algorithm? Great question. I have no idea yet because this will be finalized by the EU very soon, I think. My bet, and I will be willing to bet money that this will be enforced. This was part of what I was saying earlier, that we might need to update our informed consent because almost surely it will be made mandatory to inform the patients if their data will be used, for example, for training generative AI for synthetic data. I mean, the fact that we're using it for healthcare doesn't change that those are generative AI trained on personal data. So we need to inform the patient. Yes, I think that I cannot give certainty because I'm not trained legal expert, but from my experience and everything that I studied about these acts, I'm pretty sure that that will become mandatory and that will become a thing that we will have to put into the informed consent. Well, thank you very much for the. Our clinician currently uses AI tools and algorithms successfully or still under development? Yes, they are using tools successfully. For what I know, we still haven't really performed the AI revolution that we've been promising for 20 years. But I don't think that it can be a revolution because we need to be conservative. But day after day, we are seeing this instrument getting more and more used into the system. For example, in surgeries, there are systems nowadays that are working with augmented AI, and all of these kind of tools rely on automated identification of systems. We already have few trials for decision support rely on automatic identification. Now, of course, still there is a lot of carefulness, especially here in Europe, about using these tools because it's really easy for the clinicians to feel either deresponsibilized or dethroned in their role. But yes, we are currently using it, but it's still, I would say, in the marginal aspect. There will be, I think, few years before our system are robust enough from a numerical perspective. And from procedural perspective, we are still in the infancy of the system. I mean, if you think about everything will need to follow not only the GDPR, but also the Data Act and the AI Act, and the not even finalized. The AI Act will come into fruition in 2026. So before that, I would not expect the systems not only to be able to support them, but even to have an infrastructure to verify that we can actually support it. And nowadays, no sane person would actually regularly employ these systems in a critical situation if they cannot prove that it will be compliant to the to the systems. I don't know if it makes sense said like that. But yeah, I think that it will take a few years for it to become perceivable. Right now, it's in use, but it's still marginal. But I think that in a few years, it will become perceivable from the user perspective that these systems are actually relevant. Especially, I think that we will see more and more, probably will take at least 5 years though, in training, in medical training, in knowledge transmission from one person to the other. I think that that will become an important part.
Perfect.
Thank
Very
you,
excellent.
everyone.
So a big special thanks once again to you, Professor, for your time and your expertise and your passion. And we wish you all a great day. So thank you again for joining.